Okay, maybe it's can start.
Oh yeah.
So it's a pleasure to introduce Professor Hailiang Liu for our next track seminar. So Professor Liu is a professor in the Department of Mathematics at Iowa State University. His area of expertise is applied mathematics, and recently he has delved into some very interesting insights into a more formal analysis of machine learning, deep learning algorithms, as well as their link with dynamical systems. So look forward to the talk on mathematical problems in deep learning by Professor Liu. Please go ahead.
Okay, thank you, Pascal. Okay, let me begin to say a few words why I chose this title. So actually, last time we talked about scientific machine learning. Why scientific machine learning? I think AI is a thriving field with so many applications and active research fields. So machine learning is just the tool to that. Deep learning is just the machine learning, particular machine learning with the deep neural networks. So, however, there are lots of things application very difficult problem when you're training. There are some issues. So there is some problem. I think there is an urgent need to from mathematical point of view, to see how to solve that. That's why I feel I wanted to share some thoughts. I also think it's not only machine learning important to other fields, also very important to the applied math itself. That's why I chose this, just to share you some thoughts. That's my plan. So first, I wanted to share my thoughts, also shared by others in the community. The role played by machine learning in the modern applied mathematics. So then the second, after that, I will talk about a mathematical problem in the sense that we think, from an applied math point of view, those are very important, very urgent, as also a challenge to solve. Of course, I wish very much to learn from you. So what you see in the application of particularly your research, so where some mathematical issues you think is very important to address, I would be happy to talk to you more on that. So then after this, I will of course talk a little bit about my research, some results. Mainly there are three things. I think time permitting, I will mention the last one maybe. The first one is we use the mathematical tools from applied math called the optimal control theory to develop a model for understanding the deep neural networks. The second one is there are lots of training algorithms like SGD, stochastic gradient descent, and others. So here we have some idea with the energy. It turns out it's quite interesting. I want to share. So the last one, probably I don't have time to say that. Probably I can mention is implicit learning is kind of something very new. So the student working with me from computer science, actually, he did something very nice. Yeah, that's about the things I want to say. First, applied mathematics versus machine learning. I just say something I probably already know. Let me remind you, in the scientific research, what are main approaches? I think the first thing is the data-driven approach. It goes back to the Johannes Kepler. He found the motions of planets based on the study of data from his teacher, accumulated over 20 years. But based on that, his work actually Newton did more. The Newton's approach is just the first principle-based approach. The goal is to discover the fundamental principles that govern the world around us, which is very successful in many fields, like fluid. We have Euler equation, now state equation. In quantum mechanics, we have Schrödinger equation. There are so many other equations in different fields. They play a very important role, like wave propagation. We have Maxwell equation. So there's another guy who I think is very important for us in applied math. His name is von Neumann. So during the World War II, he started to design algorithm to help the design of the high-speed, airplane. So then that time, I think he established the concept that numerical algorithm should play serve the major bridge between mathematics and science. Over years, the applied mathematics, particularly in the US, pretty much follow the two lines. One is follow the line from Newton. So mathematics should be a language of science. So we try to get some equation to study that. The second is we design numerical algorithm, like following von Neumann. So that's the situation. So now, so what's the central difficulty for applied math problem? Actually, that you look at all the numerical algorithm we have, finite difference, finite volume, finite element, spectral method, all the methods we know so far. When we come to the high dimension, immediately we have trouble because you just partition the domain. When the dimension is so high, immediately we have trouble because the computational power is not up to that level to handle. Yeah. However, the machine learning is really very special, comes to rescue this situation, because the machine learning is to learn a function of many variables from the data. They don't partition the domain. Basically, they just from the data trying to through the network to the training. Yeah. So I think in this sense that the integration of machine learning into applied math will change both disciplines in fundamental ways. Even the machine learning is the area in computer science, now we do think the machine learning is also part of applied mathematics. Actually, indeed, it's listed last year in the Department of Energy, the program, applied math program, they put the machine learning first time there as a key area. So, so what's the main concepts in components in applied mathematics? So we have one part, so principle-based modeling, looking for physical models and analytical tools for these models. So we have all different equations and those things. Yeah, pretty much, it's my part of research. I have an equation. I before solving that, I try to use a mathematical tool to study that, to know the solution behavior. So then whether existence, uniqueness, so on and so forth, those things. The third one is algorithm. So we try to solve the equation by designing algorithms using the computer to solve the problem. Actually, data-driven method that should be also part, but it's missing in our applied math program. Even right now, we don't have courses on that. So the machine learning right now, computer science uses statistics. Statistics are already there, but it belongs to the statistics, department. They already have a very solid, the set of courses for that. Also, data processing. If we look at our courses right now, we offer to our students. So we do have a very well designed set of courses for the part 1 and part 3. So we have fundamentals of physics, say the fluid equation, all those things, the background. So applied math analysis in applied math here in our program, we have several courses. We have even a qualified exam on this part. For the numerical algorithm, we have both for discrete problem and continuous program. The different methods like finite difference, finite element, we have courses on that. But however, the one in the middle, learning from data, is not there. Actually, several years ago, I tried to introduce a course called data-driven modeling, but it seems not accepted by other faculty at that time. They said, "Oh, this very strange thing is non-traditional." Yeah, we didn't go, further with that kind of, idea. But I think that right now is probably the time to get back to that. So with this, I think that, once we have, the one learning from data, this part built into this applied math program, I think the applied math program really become a very important part. It's a form of the foundation for the interdisciplinary scientific research. At least applied math here all the main features that are particularly appealing to the young students. So simplicity and elegance of the problems, also the lots of challenges from application. So we see that we handle, using mathematics tools. That's all. Yeah, that's pretty much, I think, why, sometimes we call mathematical machine learning. So the why, the machine learning should be playing important role. I think increasingly important roles in the future, in the years to come. So what are problems in deep learning? So there are lots of problems, just from mathematical point of view, and some are really very interesting and very challenging to address. Let me just start with this graph, deep neural networks. So this is, compared to the machine learning, traditional one, the deep learning is the main difference between deep learning and machine learning. Here we use deep neural networks. You have an input layer with data. Then from one layer to next layer, each layer there are lots of neurons. Mathematically, it's very simple. You start from data, you do a data propagation. Eventually, you have a map, which depends on data, also depends on a parameter. It's called a parameterized network. It's kind of mathematical model. But then, of course, the parameter is, we need to do a training to train that. That's the general work. But what is it's magic from one layer to the next layer? There is a nonlinearity built in. It's here. I will show next slide because we have a nonlinear activation function, which play a very important role. On the other hand, you think about the human brain. So when we receive a signal from outside, so the information comes in, it gets propagation from one neuron to next, because there's a huge amount of neurons in our brain. We don't know how it works, but it works very well, right? So that's this idea. The deep neural network is kind of is a mimic of the human brain. So if we put a mathematical formulation, a neural network can be seen as a recursively defined function phi from input dimension D. The dimension is just the number of features, then to the output, depending on what kind of problem. If we have a classification, maybe this dimension, last dimension is depending on the target you want to catch. Yeah. So you see in this form, actually, you do two things. Each time, firstly, you do a linear combination of those data. Then you add a nonlinearity upon that. Then you do this again from one layer to a next layer. This is a composition. Why is this good? But our traditional numerical analysis, we do a linear space-based functions. All the series is no longer working for this case. This is nonlinear composition. But however, people already pay attention on this. See, in 1988, 89. Also, multi-layer feed forward networks are known to be a class of universal approximation. In the language of mathematics, they show that actually this kind of network, I think they showed for the two-layer network at that time. So the network is dense in the continuous set. So if you have any continuous function, you can use the network to do an approximation to represent that. Actually, it's more than that. I think they also show it's even the Meyer function is not continuous. You can do that. Yeah. So let's be more precise. What are main things involved in a deep learning problem? For a simple setting, is supervised learning. We have data. We want to learn function. So we have a function we don't know, but we have data. We know the function takes some value at these points. Can we get to know the function? Traditionally, we don't try to learn function. Instead, we do the least square, right? We assume we have a linear function. Okay, then you want to find f equal to a plus bx, find the optimal ab to pass through all those points. But the super learning can do much better, and the deep neural network can do much better than that. So let's see. Given the data set, we want to learn function. So these are main steps. I think there are three. So the first step one is we need to have a model, neural network, whatever neural network. For example, you want hidden layer network, that's good. So you can map the data to a parameterized function depending on x. The data also the parameter. So next, we need to develop a optimal strategy, optimization strategy. So for that, we need to introduce a loss function or objective function. Say for this case, we just say we sum all the distance between the value and the one you want to build a model, the value of theta at this point. You sum all of them. That we typically do in a least square problems. Then we do a training. We need to get a training algorithm. One simple one is gradient descent. You just go E time, you take a step size eta, you go to the direction, the negative gradient direction. You continue. So until you have convergence. So then you get it. So what's the total error? Mathematically, we all say, oh, what's the error? How to control that? Actually, there are 3 errors in this one. If you measure, we don't have F, but theoretically you can show that. So the error between the F, the true F, and the model is bounded by 3 things. The first is depends on the M, depends on the data size. The more data you have is better. Of course, it depends on the other things, approximation things. So the second one is you have N. What is N? N is the dimension of the parameter. That's why, when the network is getting wider or deeper, so probably you can do better because you have more freedom for you to handle. So if you have an error of this form, it's negative, alpha, beta, gamma. It depends on the model and the training algorithm. It's positive. So this one, and then the third one, it depends on the training algorithm. So what's the case at the case that we stop that after so many steps, k is large. So first order, we just have a k to the power -1 for the convex function. You see, all the when m and k goes large, then it gets small. Then we're getting closer. Around that. So of course, mathematically there are lots of problems. Mainly the way, as I mentioned earlier, how to create dimensional is the main issue, is a concern. So the question number 1. So how can we build a theory to approximate a function, right? For the continuous function, classical method in the numerical analysis courses, see we have right now. So any continuous function can be approximated by polynomials. But then you have a trouble. It depends on dimension. If dimension is high, then immediately you have a problem. Here, deep approximation of functions. There is a work in 1993 by Barrett. He proves that if the function is continuous, so if you use the one hidden layer network, so the error between the target function I mentioned earlier, the approximation error itself is bounded by 1 over squared n. It's the magic thing is that not depends on d. D is the dimension. Okay, doesn't matter the dimension is large or small. It just depends on only on the freedom of the network you have. So that's the one thing you can do, the function approximation. That's the really it's an active area in the math, applied math community. There are several groups they work on that because before they worked for the approximation theory for the using linear space. I think the second one is very important. Instead of looking at a function, now you look at the probability distribution. Why? Because each time when we train, we have only training data. Behind there's lots of data there. If there is a distribution, the distribution will be also propagated to some target. So can we learn that? Can we learn that? That of course this one you need to find a way to measure the distance between 2 probability measures. This is something that I'm doing right now in my course, optimal transport for deep learning. I offer course this semester. So I think there's lots of open problem in this part. So the third thing I think, so there will have lots of dynamic systems. So when we have a different equation, mathematically we say we clean up. It's very we just studied the solution behavior. However, the model itself, there are lots of parameters we don't know. So we need to learn from the data. I think that's so how to learn a function, but the function is the solution of different equation. So even the forward problem or the backward problem, I think this is the area. So it's very important to see how far one can go. So also, we have over years we have lots of numerical methods, very well developed numerical methods for solving, different types of partial differential equations. So when we have get to the high dimension, there is a issue with that. So can we take advantage of deep learning techniques to develop a more efficient method? So for that. Yeah, there are more problems. That's pretty much the problem. I think is within my own interest. Also, I think within the applied math community, a lot of active research groups they work on these kind of things. Yeah. So one thing I want to particularly mention is that is the there is a tool called in applied math called optimal control theory. So you have a different equation, ODE. So in ODE, there is a parameter is not given. You play as the control parameter. You need to learn that. So this one is a deep learning based algorithm. Actually, is very nature for high dimensional control problem. If one parameterizes the policy function by a neural network, then there is a very nice similarity between the optimal control and the deep learning. That's I think one could go quite further. So in using the optimal control to study the deep learning problem. So for example, the cost function of the control problem, actually you can use that loss function. It's a one-to-one correspondence. The dynamic system for the control problem places exactly the role of deep neural networks. Then the noise in the dynamic system allows us to train using the say stochastic gradient descent for training. Yeah. So I think with this, let me just do you have any comments on things I mentioned earlier before I talk about some technical results? Okay, let me continue. I want to talk about some results. I just did I think 2 years ago. I was on my sabbatical during a visit to the coast in Saudi Arabia. So I talked to Professor Peter Markovich, and actually I hosted a seminar over there on the machine learning. They like very much. Then we started to work. That's something we did. I think quite nice, and mainly on the theoretical mathematical understanding of neural networks. Let me just show you what's the idea here. So for there are lots of different problems. For example, the for classification problem, the mathematical formulation, there are 3 things. The first is we need to have a forward problem, which helps transfer the input feature in a nonlinear way to filter their information. So as the deep neural network we showed earlier, that's the forward propagation. Then of course you need to get an output layer so that if you do classification, in the end you need to find a way to give you a classification index. So that is we need to do the prediction, the class level probabilities using the features at the final output layer. So then there is a part that's very important. It's a learning problem. It's formulated to estimate the parameters of the forward propagation and the classification to approximate the data label relation. So as I mentioned earlier, typically you have a data transfer from one layer to the next layer. Roughly, you have a linear combination. Then you have a sigma. The sigma, there are different choices. One is ReLU, is just ReLU is nonlinear. It's just sigma x is x if x positive, otherwise is 0. That's ReLU. There are some other options. So then there is a special network called residual network. You add the current as a reference, then you send it to the next layer. Then you continue this procedure. Actually, in the community, people try to understand this using ODE because it's really very natural. If you rescale that, put a parameter time step. Actually, this is nothing but a forward order difference for this ODE system. When we solve this equation, we use a finite difference, right? We get exactly this one at the discrete steps. So by now, this is a fairly common procedure in the deep neural networks. There are lots of workers they play with the ODEs, but in practical applications, the dimension from one layer to another layer very significantly. So the approach we take here is not only to pose the ODE. Instead, we want to know the structure of neurons. That's really some new insight we brought in. So then with that, actually we derive a PDE. It's not exactly PDE. We have one, additional variable which describe the neuron. We call that neuron identifier. Then T is denotes the depth of the network. Then sigma is the nonlinear activation function. So for a particular model, you have that. So then we have two functions. One is B, depending on where Z is called a selection weight function. So and A is the Bayes function. This is pretty much is a mimic the discrete verb, but mathematically say why is that discrete model is close to that. There is a way to do that. So actually, the first thing we did is how we came up with this model. What's the basic assumptions on those things so that the problem is well posed. So actually, we borrowed the idea from the multi-particle physics. So like in the fluid equation, in a rare case, there are so many particles. When the number of particles is huge, so you want to pass the limit, you want to develop the continuous model. So this is pretty much the thermodynamic limit about. So I'm not going to touch all the details. Basically, we have a way to do that. For example, we start from a network of fixed widths. Then we define the piecewise linear function so that we do interpolation. We just close. We link one value to the next value. So then we find a way to pass the limit. Yeah, there's a very nice procedure. We can prove that this is the theorem written in the mathematical way. So the solution of this one, even is piecewise linear. So when this layer goes to infinity or tail goes to zero, actually the solution indeed converges to this equation ODE. But this is a continuous only in time. It's still discrete in the other direction for the neurons. So we can go further. Do a limit, just let n go to infinity. What's the n is the number of neurons in each layer. Of course, each layer the number is different, but here for simplicity we just take the same. Even different, if different, we need to adjust a little bit. So we do a very similar, procedure. We partition the Y into cube cells, the YG with H. Then in those equations, we define again the function, which is you have a different parts of function, which is the different piecewise continuous function, so that these functions satisfy this equation in each cell. So then we pass the limit again. It's roughly that's the idea. Actually, this is a very powerful tool in the study of mean field limit of any type in multi-scale physics. There are lots of continuous PDE models derived in this manner. So of course, with that model, of course, we had a theory. We studied the well-posedness and we identify a condition for the AB. Very beautiful. I'm not going to show those. This is very mathematical, those things. Instead, I continue to tell you something about the control of the problem. How can we do the that's a forward problem is well posed with some condition. So how about we do the learning? So learning problem is pretty much is the control problem. So what is the control problem? So you see, we have a loss function. So between the f and the target. So we wanted to minimize this loss function. So what is the constraint? Constraint is the neural network. Right now, I have a continuous version of the network. Basically, we wanted to minimize this function subject to this differential equation. That's all. But however, this problem is rather challenging for several reasons. First is the high dimension, also non-convex problem. It's a constraint optimization, high dimension, non-convex. So that's if you are familiar with the optimization, those things, it's really a lot of challenging problem here. Computer costs, for example, are high. Also, we need a very deep architecture because we pass limit. It means there are so many layers. So also these structures are prone to various problems in the training process. So besides that problem, I wanted to say, mathematically, can we come up with ways to see how to train that more efficiently? Actually, in the context of optimal control, we can see there are 3 ways to do that. The first, we can do the gradient descent, but we need to find the gradient. So what's the gradient? Typically, you do a back propagation in the context of deep learning. But here, actually, if we follow the control theory, we can introduce a backward problem, a joint problem. It's a forward problem here in level A. We have a GL depends on AB is a parameter. Then we have this problem, the forward problem, backward problem. We can derive that after we solve this one. Actually, this formula. We have a gradient of this function in terms of A, also in terms of B. This process. Basically, the algorithm is clear. We just solve this equation forward and backward. We do an iteration each time. We use this gradient. We do the gradient descent. But however, when you combine this one, the problem here we have not done yet is mathematically. So what's the convergence? And how fast is the convergence? Yeah. So at least from a practical point of view, this gives you a way to compute the gradient to apply the training algorithm. So that's the one way. If we write an algorithm using this idea, pretty much that's you can update A first. With this minimization, actually this one spatial form is the proximal point algorithm is more stable. It's the way to do that. Then we solve for F. Then we get we need to get also the forward backward, because that's how we get a deep gradient. You know, gradient when we solve this equation. So that's the step 1. It's not so much different from the Euro practice, but what's new here? I mean, new is for the model I talk about. Also, they are already used for the by others, for some problems, of that type. But for the model I mentioned, so there is a way to do a polynomial maximum principle. This is also very well known in the optimal control. So it means, so instead of doing minimization, we introduce a function, a kind of Hamiltonian. So the Hamiltonian is defined of this way. We do a maximization eventually. So this problem is equivalent to the following. We solve the forward problem to get F. We solve the backward to get R. It's a constant variable. Actually, after we get FR, what is the optimal A star, B star? Actually, you only need to do a maximization of a Hamiltonian. Yeah. So the Hamiltonian is given because after you do the computation, one iteration, you have all of those. Also, this good is we don't need to worry about this gradient, to use that gradient. This one based purely on the Hamiltonian. See, that's the algorithm. The forward problem, there's a backward problem. Then we update this one, we get the next one. So there is an issue here. Okay. What's the issue? The issue is this is only a necessary condition. It's not a sufficient condition. So in practice, you would have to use some suitable way to regularize so that it becomes stable. Yeah, stable. But in general, if a problem is simple, probably you can handle. But in general, there is an issue to regularize to make it more stable. Yeah. Okay, the third one. The third one is a very beautiful mathematically. Actually, you can do this way. You consider this problem. Is instead of consider only one data, instead I consider a set of data, a fluid. Like the data it depends on any time t. I have arbitrary data, depends on y in the neuron dimension. So this is typical way people handle in the optimal control. It's called dynamic programming principle. If you do that, actually you can consider this loss function. Even you can do more. If you have a data from application, you say, oh, I have a data. It's time series data, like COVID-19, right? We have data, public data, every day is updated. Then you can put here. You get the running cost put together. Then, if we define the value of this functional, So in terms of AB, actually this F satisfy Hamilton-Jacobi-Berman equation. This one. So mathematically, what is good? The good is this equation allows us to identify optimal control, hence give a necessary and sufficient condition for optimality of the learning problem. If you can manage to solve this problem, actually that's all you need. You no more than that. But what's the issue here? Issue, of course, is you go to even higher dimension, because originally you have a very high dimensional problem, right? You sample data, you try to reduce the computer cost. So currently we are trying really to find a way to put this into a more practical algorithm, so that we can combine the one earlier, the maximum principle and this global one. That is the local one, along characteristic. This is the global one. There's some ideas how to do. I think this is not practical. Just what's the way mathematically to do that? Yeah, to find an optimal. So if we follow this procedure, actually in the end, the A star B star will obtain here is indeed we can prove it is optimal. It's optimal. Okay, let's see. Let me a summary. I think that this part I talk about model, PDE model is new, and it's so we still try to understand and then to extend it to further applications. I think it involves three simple ingredients. The first is the basic structure in the neural networks, affine transformation, linear one and nonlinear activation. The second one we have from layer to layer we have a depth limit. So another one we have neural interaction. Basically, this serves a very good model to do a more careful study of the neural network structure for particular neural network. This I talk about only one network, but if you have a different neural network, I think something similar can be done. But of course, the analysis could be difficult. I think this give you a way, the model itself is able to express selection, propagation, and the control of network parameters. So we also provide ways for solving the learning problem. I think there is more work to be done to make those things more efficient as a practical algorithm for each corresponding to each path. Yeah. Let's see. Do you have any question about this optimal control things? Okay, let's see. I have 2 more minutes. Let me get to the next one, the gradient method. So earlier we talked about 3 things. Approximation, that's a different thing. You think about it, you have network. You have function is not in that set of network. Of course, you want to know how good the network is to approximate the function. It's a purely mathematical problem. Then we have a generalization. Generalization, it depends on when you sample the data. So whether you find a way to sample efficiently so that you can really get a data which represent all more the information there. But I think that essentially there is one part is the training, because the problem is so complex. So we need to come up with some training algorithm which is efficient, which is robust, which can handle many situations, because it's like a black box. We don't know whether it's convex. Typically, it's not convex, even not smooth, the loss function. Yeah. So we got some idea. I wanted to share with you the gradient with the energy. People talk about the momentum. I think we talk about the energy. I will show you this slide. So first, the problem setup. We consider the finite sum optimization problem. This is typical from a neural network. As I mentioned, you have a data, you want to learn a function. So yeah, pretty much this Fi is the corresponding each data. What's the loss function? We just do a sum over all the data you have, a training data set. So that's the function we want to conceive. I've seen of this form. So the only assumption we assume is that f is bounded from below, because that's we wanted to find a minimizer. F is differentiable. It's not essential, but mathematically say if we assume that we can we can prove lots of good theorems. Yeah, even when I don't show you all those results here. So we propose a novel algorithm, so using energy, and there are some corresponding some theoretical results, such as stability, convergence rates, energy bound for non-convex functions in particular. Let me just tell you what's the idea here. So we all know the method gradient descent, right? You just each time you choose one step in negative gradient direction, you move. It's very simple to do implementation, but it's stable only for small step size. If you take a large, then you have trouble. Okay, there's some issues with that. So there's another one. Then you do, I do IF is not evaluated as K at a still negative direction, but evaluated at the next step, which I don't know. So if you do that, actually this one stability is much better because IF theta K decrease monotonically for any step size. What you need to do is, this is nonlinear. So you give you an additional task, how to find the root of nonlinear function, right? That one. So that's not good. Now the question we ask is, can we adapt the vanilla, this form, the GD, and improve convergence and stability with arbitrary step size, as in the implicit scheme? This implicit scheme is independent of step size, but more stable, but it's not easy to compute. We want something is easy to compute like the first one, but it's as good as the second one. Okay, that's the question. So the trends we found one is very nice. That's the idea. This is the key idea here. So because as FC is bounded from below, I lift so that it becomes positive. I introduce a new function called G. I transform this function to G. I got a G is greater than F plus C. Because the F plus C positive, this is well defined. Then I introduce R. If I do R, then actually we have a following notation. So the earlier method, if you pass the limit, even go to 0, actually you solve this gradient flow for the equation. But this gradient flow with this new formulation can be rewritten as this form. So based on this form, I write down this scheme. I just do the final difference. It's very simple. That's not very simple. Okay, you see, when I discretize, I have a trick. I do R as the implicit RK plus 1. I do G is nonlinear. I do a theta kernel. I just play the game, to find a balance between implicit and explicit so that it become unconditionally stable. Then we have R here. The question is, this is not easy to compute. No, it's easy. So let's see. From that one, actually, I rewrite. I combine two formulas. The R you have a formula. It's very simple. RK plus 1 is RK over Z. Each time you have RK theta K, you just get RK plus 1. You plug in into the second equation, you update the theta K. It's easy to compute. I don't write down a theorem. We have lots of theorems. Good here. But it's it's unconditional energy stable. It means R is going down. But what is R? R is the gradient of F. It's going down. F, we don't know whether it's going down monotonically, but it should be in that direction. Yeah. But we found that in practice, we should do also energy in each direction, which is better. That's the way element-wise AEGD. Just in each direction, we have a energy in that direction. In practice, it's this one element-wise one is better. But in theory, we have a theorems, all those convergence stability for both schemes. That's what I mentioned. Actually, beyond this scheme, we did a lot in the past year or so, 2 years. I think we work on this one. We developed this into a statistical version. We also added momentum upon that. We developed a series of theoretical results, unconditional energy stable, are going down, and convergence rates for non-convex loss functions, convergence rates for online optimization, particularly in all those estimates, it depends on R. If R goes down 0 too fast, okay, In practice, we didn't find it that way, but it's a theory. In theory, this is still a issue for us. We still work on that. But actually, under some sufficient condition, it is arbitrary but not so large. So we can show Rk is strictly positive. Yeah. We did lots of experiments. Let me just quickly show what stochastic AGD as yeah, pretty much we use the formula. Is here I just each time I just take a sample from a data that typically in a SGD. So I do here, but also you see my G is transformed the origin function. When I do a sample for the gradient, I also sample from the F itself. Yeah, that's different from the SGD. Yeah. So then we also did things extend that AGD further to the momentum. So the way to do that is just instead of using this gradient G, we just replace this by accumulation of the gradient. You just M0 is 0. You just add a factor. Eventually, it's kind of you take the recent average of the gradients you use. That typically can speed up the convergence. Also, because you have mu less than 1, the more recent one play more important roles. So actually, that's some more work we are working right now. Actually, so that's another way to do right. Before here, I think we had a paper we used in the R we don't use the M. So instead, if I rewrite it here, for R and theta, I use same VK. The only thing I play with VK if with this formulation. So all the unconditional stability, all those things I mentioned earlier, this remain valid. So actually, from the study of a continuous version, this one we found a lot of good things. The exponential convergence rate with non-converse function with some structural condition, typically, which is the case for many neural networks. Yeah, I think it's a very interesting algorithm. I would think that if you have something you like to try, I would be happy to share with you more on that, our progress on that. Let me quickly show you some I think 2 slides. This. You can see this is the comparison between the gradient descent with momentum. This is the green one. This is the AEGD. This is the AEGD with momentum. You see, with momentum is much better. If we go to this one, we look at the trajectory. I think that trajectory is if you have a gradient descent with momentum, so the trajectory goes this one. It's a detour. After some time it gets back to the main measure. Here is getting. I think it's the red one is this, with energy and momentum. From here you see some advantage. We show this one.
So here gradient descent, you mean stochastic gradient descent, or not?
No, this one
batch level.
I'm not sure this is good. Yeah, we did a stochastic gradient descent because in this case we added noise. I'm not sure exactly this one is with SGD. Yeah.
Okay.
Yeah. But this one is with the stochastic version, because this is for the neural network. I think I particularly wanted to share with you. You see, the generalization performance is one main concern. So we found that actually this one AGD has a better generalization performance. We compare with lots of algorithms. For example, a very well-known one called Adam. But Adam is known because that adaptive nature, the generalization performance is not that good. But the gradient descent with momentum is good. But we see this AGDM is better, or at least as good as the gradient descent with momentum. Yeah. So our initial, as I mentioned, because there is unconditional stable, is also initial is faster, like Adam. Yeah. Yeah, you can see this one is the performance. Particularly, I think a good thing is about the generalization performance. Let's see.
It's interesting to see that you see that jump at 150 epoch for all of them. That's
Which one?
The jump in accuracy that you see after 150 epochs.
Oh, okay.
That's an interesting observation, and you see that everywhere. That's interesting.
No, this jump, I think there's the first part is
Do
just
you change the rates or something, learning rate? Or
no,
something?
you change the you shipping here. Shipping now here.
Yes, I'm
Oh,
here.
shipping, can you
Oh,
explain?
yeah.
Okay.
Sure. So the jump here is because of the learning rate decay schedule.
Yeah,
at
so you change the
epoch
learning rate.
150. Yeah,
Yeah,
it
okay.
is.
Okay, and you do that for all the methods that you compare, right?
Yes, for all methods.
Okay.
So
Another question on the same lines. So you're just using one learning rate decay here, not 2 or 3.
Yes, just one learning rate decay at the epoch 150.
Sure.
So basically, you have one learning rate about 150, then you add some decay rate, something typical. Yeah. That. Okay, I think here just a quick summary. We have a novel gradient based optimization. I think mainly new thing is energy. We do indeed it's still adaptive, but use through energy. Yeah, suitable for solving large scale optimization problems. Is unconditional energy stable is particularly is attractive feature for this method. So I think there's some potential we can see for training deep neural networks with better generalization. Yeah. So with this, let's see. I think I said I want to show you this one. This is from Qianxian Gao from computer science. Last year, maybe earlier, he got interested in deep learning, but he got interested in the mathematical theory of deep learning. I was very impressed. I started working with him. Actually, recently he got the paper. The paper is accepted by a conference journal just 3 days ago by the ICCR. Which one? Yeah. So it's his work. I have only 2 slides to show you. So there's something, different neural networks. Recently, people pay attention to something called implicit layer. Implicit layer, there's some advantage because there's many problems that can be put into a way of doing implicit layer. See, you have ODE, you have PDE, you have optimization. You can think that as an implicit layer. So that's he did the global convergence theory for that. Let me just show you some. It's kind of technical terms, lots of things. So I guess I wanted to show what is the implicit layer is this one. Yeah, you have a Z here, you have a Z here. So you have just this way. But of course, when you're gonna do this one, you need to do an iteration, but it itself is defined by an implicit function. So what you can train, you just use the same A. I think you save computational cost. It's not every layer you have parameters. You use the same set of parameters for all layers. There's no layers. Actually, the infinite many layers. If you expand this implicit layer. So for this setup, if we consider previous problem is like a data to learn function. So with this setup, and our theta is this one. As that's what is the U? I think the U is do I have this? No, okay. That's I said is you have hidden layers. You need to do an output depending on the particular application. That's we have additional variable U and V, and A and W is the parameter in the network here. So that's his result. So he shows that this implicit layer, of course, there is an issue whether you have a solution. He shows that if you initially randomly choose the data in some proper way, actually the problem is well posed. In addition to that, so he shows that if all these parameters are randomly initialized by some sub-Gaussian random variable, if we set M to be of this size, so you need to get enough which is M, Earlier I used different. So n is the number of here data, m is the dimension of the parameter. Yeah. If m, so you have number of parameters of this size is then we have a exponential convergence. Yeah. This is quite remarkable. I think that's there is a potential to go further in this direction. Just to see, he use gradient descent. Say for example, if you don't use gradient, you use others, whether something can be established in that manner. Yeah, I think with this, let me stop here. Yeah, that's all I have to say.
Excellent stuff, Hailiang. I really
Okay.
appreciate it.
A couple of questions I had.
Go ahead, I.
Yeah, Professor Hailiang, in the for the last part of the deep implicit layers and all, are you considering the deep equilibrium models over here, or some other kinds of models like the flow models or other implicit networks as well?
You mean this one?
Yeah.
No, this one is there's no particular flow model. It's just this one, implicit layer. Say basically earlier we say z equal to f theta x. Here just z equal to f theta x depends on the implicit manner. This is just a particular form of that network. For that particular one, actually he can establish that theory. Yeah. Did I answer your question? I think for there are different implicit layers people introduced recently. Yeah.
Right.
Yeah.
So this is the equilibrium one, I think.
Yeah, the equilibrium one.
Yeah.
Yeah, got it.
No, you actually when they say implicit layer, they just mean this one. Okay. But to find z, you need to expand the layer. There's no layer. It's just implicit layer, just this one. Yeah, kind of equilibrium equation. Yeah.
Yeah.
But then you can find a way. Actually, there's a freedom to design a way to find a z. Then that give you a iteration, right? Like different layers. Yeah.
Right.
You had another question, I thought.
Yeah. So in the beginning of the talk, you decompose the loss bit, the fitting loss into 3 terms. I did not particularly find the network architecture coming out in that loss. Like you had one for the data, one for the training algorithm, one for the network number of parameters. But like the architecture itself, for example, if you're using a fully connected layer or a convolution layer, or what kind of a topology of your architecture you're using doesn't show up in this performance. So
so this one is very rough. Actually, in order to derive this, actually this one is too rough because I didn't specify what's the norm.
Right.
If we do the in R2 norm or for in energy, I need really to do a more precise. But this just indicate that if we do this f minus f theta, we need to go back from here to a continuous version.
Okay.
So from continuous version, you take sample when you do the data. So there is a need to see what's the error from that part. Say for example, if you have an integration over a domain, right? You just randomly put some points. Then those points play the role as the training data. Then you get this one. So immediately there is an error between error theta, the discrete version, and the continuous one. There are lots of things going on, but here is a very naive way just to say any problem of this type. Actually, there are 3 types of error involved.
Okay.
Yeah.
Got it.
Great. Any other questions? Okay, if not, thanks again, Hailiang. Really appreciate it.
Okay, my
yeah,
pleasure.
and we'll gather again next week with another talk, new talk. Thank you, everyone. See you next week.
Okay, bye-bye.
Bye.